So working here on this wave versus particle duality, page 9, we're gonna be looking here at our teacher demo, where what I'm gonna try to do is I'm gonna have this laser, that's this guy, and the laser is gonna shine onto this thing called a diffraction grating. And then with this diffraction grating, there's gonna be something interesting that's gonna happen. So I'm gonna take this light, I can shine it on this paper, I can move it around, I can make circles, I can play here for a minute, and I would really enjoy it. I can also take this diffraction grating. You can see it's see-through. You can see like my hand. You can see my ring through it. You can see through this diffraction grating. But what happens when I take this laser and now I'm going to make the laser go through this diffraction grating. It's taking this laser. It's making something interesting. So as I take this laser, it does some pretty cool stuff here. So depending on even how I hold this, you get a different looking pattern. How this gets bent and shifted and moved, you get a different looking pattern. But you see some pretty cool stuff to where without the diffraction grating, we just get the plain single point. But with this diffraction grating, you get something more. So for you, we have this here. I want you to try to draw out what it is that you're seeing. Draw what you saw. So as I'm taking this diffraction grating, having the laser, so I'm gonna give you a minute to draw what you saw. So once you draw this out, where you have the laser, a diffraction grating, and the wall, and hopefully you drew out something what you saw, I want you to try to explain why you think there are multiple areas of this intensity. There's no right or wrong answer here, except no answer. I want to know why you think it. Nice. So I get someone here telling me that they're thinking it's similar to that triangle thing that splits light into a spectrum of light. That uses refraction. So that's slightly different, but using the same principle. That it gets down to that light has a constant speed in a given medium. And so when it goes into the triangle thing, that's called a prism. When it goes into a prism, light goes at a different speed inside a prism than it does in the air. And so then it spreads out those light beams so that way we're able to see all these colors. Here, diffraction also uses something similar to where light also has a constant speed in this medium, which is the air, but it's not changing the mediums. It's actually only going through the air and passing through this diffraction grating. But it's similar because it is using similar process. So does anyone else know why it happens? It's similar to that. That's also using refraction. So if you, in a rainbow, that uses refraction. So that's just like that triangle thing. That's just like that prism that will spread out light. But there's a difference between diffraction and refraction. But I really love rainbows. I like this one. So someone came in and said, maybe a filter inside the grating that causes the light to split without losing intensity. Ooh, I like that. I like that. You're actually close to being on the same track, on the right track, but it's even more intense than that. Ooh, it splits all the wavelengths. I like that one too. That's pretty cool. It's actually, now we're getting onto the right track. We're not exactly there yet, but we're on the right track. All right, so now that we have what you think, the source of our wave was the laser pointer. And the purpose of this diffraction grating was to make multiple waves we were to make multiple waves from one wave with the same frequency. We've looked a little bit into what frequency is. That's really what we've been focusing on. And that's the number of times per second, the oscillations per second. So we have an idea that waves with frequency, and if a wave has the same frequency as another wave, then they're pretty much the same color. Or if it's sound, it's the same pitch. So we're making multiple waves from one wave with the same frequency. That's really the point of this. So what I'm going to do is I'm going to take us over to this simulation I got. In this simulation, I have here, I can look at some waves and I can create a wave on water. And if I have a droplet hit water, then we see that it makes these waves go throughout all the space. And then I can change this and I can look at this thing called interference, where I turn these on and they fall, these water droplets fall at the same frequency. They're dropping at the same number of times per second. And what we see then is we have this one wave go out, and then we have this point where these waves build up. They build up and they make a higher wave than originally. And then these darker parts where these waves interfere and they destroy one another. And then when they destroy one another, it makes a dark point, or in this case, where there's no wave. And then we can get to these slits over here. So I have only one slit. So I can make a wave. As this wave goes through the medium, it will hit this slit, and then some of the wave will go through it. As some of this wave goes through this slit, it then spreads out. That's what diffraction is. If you've ever been to the ocean and you've seen a wave hit like a pier or something, you've experienced diffraction. That's just where this wave comes out and it spreads out to where this wave coming from this slit is able to go up and up, where before the wave was only going to the right. Now some of the wave is going up. So that's this diffraction of light, or of waves. I can then add in two slits. When I do this, now I'm making two waves with the same frequency, just like with those water droplets. And I'm seeing the same thing where I get these bright points where there's a bigger wave, and I get these dark points where there's less of a wave. I can change the frequency. So then we see a different pattern show up as a result as well. But the bright points, that's where we have a bigger wave. The darker points, that's where we have no wave. So this leads us here to this thing of diffraction, where I can turn on the laser. As I turn on this laser, I can change the wavelength of it, and that changes the pattern. That's just changing the frequency, the color here. I can change that. I can also change what the laser goes through. As the laser goes through something different looking, I get a different looking pattern. As I get a different looking pattern, I can change even how this shape looks. I can change the height and I get a different looking pattern. I can change the width and I get a different looking pattern. All the pattern tells me, when I look at this, I see it, it tells me exactly what this shape is. And so then I can look at this here. I can see a lattice of material. I can increase the spacing and I get a different look to my pattern. I can change the diameter here to be big or small, and I get a different looking pattern. This is very similar to the diffraction of looking at those materials. When I said I had to find something that was 1 atom thick, I had to look for something. And if I saw a pattern that looked like this, then it's telling me I have more than 1 atom in there. I needed 1 atom thick. I needed a pattern that looked closer to this. And when I saw a pattern that looked closer to this, then this told me that I'm looking at something that's more like an atom. Now, atoms aren't perfectly circular. So they do form like different looking shapes. And the atoms themselves, they form different patterns too, because they're not, well, circles or squares. And so I had to find a pattern that looked, well, specifically the way I wanted it to. And that was to show me that I had a 1 atom thick layer of material. But depending on what the laser goes through, then those waves interfere and make these bright spots, or they interfere and they make these dark spots. When they interfere, they add up. That means those peaks and peaks make a brighter wave. And where it gets dark, that's where a peak and a trough cancel each other out to make no wave. And so these patterns result from the laser going through this diffraction grating. So we saw a little bit about this diffraction and what happens with this diffraction grating. We might have a better idea that the why we think this has to do something with the interference of waves. And what I mean by interference of waves is if I have a wave and another wave like this is going to create a bigger wave. If I have a wave like this, what's going to happen is it's going to cancel each other out. So when I have a peak and a trough, they add together to give me nothing. And a trough and a peak add together to get me nothing. But a peak and a peak gets bigger peak. A trough and a trough gets a bigger trough. So this amplitude of the wave is affected by this interference here. And this only can happen when light is a wave. So we know light has to be a wave here. So what we're going to do next is we're going to get down to here this Dr. Quantum. Dr. Quantum is a really good friend of mine. He's actually one of like my best friends. He was one of my roommates in college. We go way back. Actually, like we still text one another. And so what I'm going to do is I have a video. I'm going to play this video, and I'm also going to give this video to you in the chat. So I'm going to put the video into the chat. And as I do that, I want you to watch it. I'm going to watch it as well. I'm just going to turn mine on mute so you don't have to hear me. And then after we do that, we're going to come back and we're going to try to answer these questions. So I'm going to put into the chat our video. And then we're going to open up that video and try our best to answer this. All right, everyone, so let's bring it on back now. So we got a chance to talk, or we got a chance to hear what this Dr. Quantum was saying about these marbles being shot from this double slit. And so he got there's some pretty cool stuff that he was talking about. And if we saw at the 1 minute and 10-second mark, that's really right around where he started talking about what we classically expect from these marbles. So what we classically expect is we expect two bands on that wall. And really, it's getting to a particle model. Because really, when you shot electrons through or shot something through that slit, or marbles, they're not waves, right? You don't see a wave on it, but you expected to have one go through one side, the left, and then make a left band, and then the one to go through the right side to make the right band. But that's not what we saw. We know that actually something different happened. And then when we had with just the water waves, right around the minute 40 mark, that's where we saw that these water waves, they interfere. They interfere and they make bigger waves. So when they actually did send these electrons through that double slit, these electrons, they made a diffraction pattern. They made a diffraction interference pattern. Really, that has to be explained only with a wave model. So we classically expect these marbles to be shot from this double slit to form two bands on the wall. That's that particle model. But we really know that they interfere with one another. And when they interfere, they make this interference pattern, which can only be explained by this wave model. So we're getting asked this question, does an electron behave like a particle or a wave? Well, it's tough to answer that. And what I want to try to do is I'm going to get into two things. One, I'm going to start talking about Schrödinger's cat. So Schrödinger's cat is a thought experiment. A lot of time people just think that Schrödinger's cat is just an abuse towards cats. Well, what it is it's a thought experiment when you look at this. Really what it's saying is we're being asked the question, is a cat dead or is a cat alive? And we have a cat inside this box. And when this cat is inside this box, there's this vial of radioactive material and a vial of other stuff that as soon as the box is open, the cat is immediately killed. So if you open the box, the cat dies. But you're asked, well, is the cat dead or alive? So then, well, what if I just shake it and then the cat will make a sound? Well, if you shake it, the vial breaks and the cat dies. Well, all right, well, what if I send x-rays through so that way I can see, the cat and what he's doing? Well, as soon as you do that, then the vial breaks and the cat dies. So really what it is, in this thought experiment, is if you make a measurement onto experiment, you are becoming part of the experiment itself. As you are the observer, and you are looking into an experiment, you affect it. You become part of it. So there is no experiment that is done that does not have also some effect of humans or the observer affecting that experiment. Perspective is reality. But in this thought experiment, it's not about killing cats. It's about being an observer. And if you open up a box, then you affect the experiment in that box. What you're saying is that cat dead or alive. If you open it, you decide that the cat is dead. So this is a pretty confusing mind experiment. So I have someone else here that also does a really good job at explaining this. So we have a 2-minute video I want you to try to watch here. It's with one of my favorite physicists that we can view, we can see and hear. So I'm posting this along here to us. That way we can get this Neil deGrasse Tyson. I love this guy. I want us to just watch this video real quick, and then this will help give us some more in-depth into what we were just looking at. I'm going to watch this video, and I'm going to mute myself so that way you guys can watch it on your own. And then we're going to come back after this video. All right, let's bring it on back now. So down here to this last part, I want you to tell me if an electron will behave like a particle or will it behave like a wave? Now we saw in that when you watch those light particles, that when you watched it, it formed these two bands on the wall, which showed us the particle model. And then when we weren't looking at the light particles, then it formed this diffraction interference pattern, which is described by the wave model. So I want you to tell me if it behaves like a particle or like a wave, and just tell me which one you're thinking. So I'm gonna give you guys like a minute to try to write that up. All right, so hopefully you're able to decide whether you think it's a wave, it's a particle. Well, it behaves like a wave, but it also behaves like a particle. So what we've done so far is we've looked really at how a wave could be a particle. Yes, it can be both a wave, but it could be both a wave and a particle, but it could also be only a particle and only a wave. Like with this interference pattern, an interference pattern cannot be described by a particle. And what I mean by that is only a wave can have it to where one wave and another wave cancels out when they interact like this, or a one wave and another wave make a bigger wave. If I were to take a tennis ball and bounce another tennis ball on it, it wouldn't make a bigger tennis ball. the tennis balls would just bounce off of one another. That's what a particle is going to do. A particle is going to bounce off of another particle. A wave will take one wave and another and make a bigger wave out of it. So light can only be a wave then. So what I'm going to take us to is I've given you this site, this hyperphysics site. And what I want you to do is I want you to look at the photoelectric effect. And this photoelectric effect is going to give us some cool stuff here. Really, on this, what I want us to first get with the photoelectric effect is that light with this photoelectric effect, light has to be a particle. So we had this one site here, and it gets into this wave-particle duality of light. And so they talks here about this photoelectric effect. And when these photons come down, they hit these electrons and they bounce off. And they bounce off with a specific amount of energy. You can increase the intensity of the light, adding more energy to the light, but the electrons that get emitted will keep the same amount of energy, regardless of that intensity. So there's some things we can get here that electrons are going to be emitted immediately when these light particles hit these electrons and eject them. Different frequencies will not necessarily make all electrons move. Only specific frequencies actually work. And these frequencies are different energies. So only certain energies of light will make the energy of this electron come out. What the photoelectric effect is it's really a solar panel. Light hits a solar panel, it knocks electrons, makes those electrons move, which is electricity. And so we see this photoelectric effect that really shows that light has to be a particle. And they also get down here about this wave-particle duality of light, that there's different things that can only be described by a wave, like reflection and refraction, interference. But particles, you can't have particles interfere. You can't have particles diffract. You can't have particles polarize, but you can have particles do this photoelectric effect. A wave would go right through these materials and would not interact with those electrons. So a wave cannot describe this photoelectric effect. Only particles. So that's what all this is saying here. So as I come back to our assignment, one of the things that I was seeing was that light has to be a particle because a photon, that's a particle of light. It will hit and bounce off of an electron. For this third thing, I want you to use that site, and I want you to find something that you get from this. So I'm gonna give us about a couple minutes here to try to find something that you get from that one site. All right, so let's all bring it on back now. So I put into the chat this site up here. What I'm trying to give us is the site for this down here. So we're going to look at this, and what I want you to do is I want you to draw for the screen and the screen chart, where I even tried to write into the chat that for this diffraction, the screen is going to be the left image and the right image will be that interference pattern that you're going to put here onto the screen chart. And what I mean by that is once you get to this site, I want you to get to the diffraction spot. And from here, you got to turn on the laser. And this left image, that's that screen. The right image is the screen chart. I know they don't look exactly the same, but that's okay. What I want you to try to do is try to draw the diffraction pattern that happens as a result from this image. So you can change the image that you want to draw. And then draw the interference pattern as a result. And you're going to be putting that down here onto this bottom part. So once again, we're going to have on here, right below the hyperphysics, we're going to have this screen right below and the screen chart right below. I know they look slightly different, but that's okay. What we're going to do in both is we're going to try to draw what it is that we're seeing. So on this left, we have the left, and on the right, we're going to put the right one. So with respect to this over here, we have the left and we have the right. And you can decide which image you want to try to draw, where you could draw the left and then draw the right. So I know a lot of you are already done with your drawing. The last thing I'm going to have you do before you go here today is this waves question number 5. So this waves question number 5, this is where we're going to have waves add together, cancel each other out for this double slit experiment. We also have the photoelectric effect where light comes in, the photons of light, and knock electrons off to create a voltage. And I want you to use both of these experiments to say, how does light act like a wave and how does light act like a particle?